So today we are going to talk about basis and dimension. So let's give a kind of a general overview, and then we go to the definition. Let's go back to the situation where you have one vector, and the question is, what is the span of that single vector by itself? Meaning the set of all linear combination of this guy. There you have one vector. All that you can build out of it is multiples of it, double, triple, or multiplying by any kind of a number. Well, the set of all those multiples here, like you double it and then you perhaps triple it, and in between you also multiply by all fractional numbers as well, maybe negative numbers and so on, and this set together is just that line. So you can say that that original vector you had, this is a basis for this space. So this is the basis. It spans this vector space. Now if somebody had brought this and in that basket and also placed a second one of the members of this vector space, you could say that one of them is redundant. You can throw away one of these guys and just keep one, because one of them does the whole job. So the idea of basis is to capture the minimum number of vectors you need, whose linear combination is going to create your entire space. Let's go try this thing again. Suppose you are given a basket of vectors which has this vector in it and say this other vector in it. Okay, so you have this vector v1, v2. What's a linear combination of these? Meaning multiply this by any number you want. That's going to be like a vector like this. Multiply this by any number you want. There's going to be another line like this. Add any two elements of these two. What do you get out of doing that? You get a plane. Now, none of these two is going to be considered as a fact that you can trim. If you trim V2, what do you get? The space that is spanned by V1 is just a line. If you trim V1, all you get is another line along V2. You need both of these to generate this vector space. So here you got this vector space that is spanned by these two vectors. Neither of these guys could be trimmed off. So this set is going to be considered as the basis. Now, if in your original basket somebody had included another vector, okay, so like this blue vector. Now, the linear combination of these three vectors is still that vector space, but now one of them could be considered redundant. Is that right? If I didn't have V2, I still had this whole plane, and if I put this V2 in the picture, well, I'm still covering the same space. So this one couldn't be considered redundant, or if you wish, V1 or V2 could be considered redundant. So when you have a basket of vectors, many times it happens that some of them could be trimmed off, and the rest of them will still reproduce the same vector space as before. It's like you have some redundancies here. And the question is to flag them out and know in advance that some of them could be taken out without damaging the whole structure. So this is a basis, or these two, but you don't need all three. What is the idea of a basis? You have to have a basis first we start with a vector space. So a collection of vectors is considered a let me rephrase. Given a vector space V, then B as a collection of vectors is considered a basis for V if two conditions are satisfied. B is linearly independent and part B is that B spans V. So if you want to be basis of something, first of all you should be able to build that from your basis, and second thing, that basis should be linearly independent, meaning none of them could be replaced by a combination of the others. Let's take a look at some easy basis, some example of an easy basis. Suppose you have this, your ordinary R2, set of all vectors in the plane. What would constitute a nice simple basis for it? There is a basis that's very famous, so you use it in calculus quite often. If you have taken calculus 2 or 3, you know this is the nicest basis you can work with, and they have special names for them. What are these vectors called? X and Y coordinates, I and J. Sometimes they call them I and J, or in anticipation of dealing with higher dimensional spaces where you're going to run out of these IJKs. You know, what if we had 100 of them? Sometimes they call this E1, E2, or sometimes they write E1, E2, different styles of writing them. Well, let's just stick to I and J. So who is I? I is the vector 1, 0. J is the vector 0, 1. First of all, any vector in this space can be built out of them, and the nice thing about this is that it's very easy. Suppose I had a vector, say 7 and 5. How can you build 7, 5 out of I and J? Simply is take 7 of this, 7 step to the right, that's just how you say it, 7 step to the right, 5 step up, is 7 of these type of steps and 5 of those type of steps, so 7I plus 5J. So writing these vectors using I and J is very trivial, just tells you how many of these things you need. So if you had X, Y, it's very easy, it's Xi plus Yj. That tells us, what does it tell us? That Ij span entire R2. Anything in R2 is a combination of I and J. So first of all, we have this property. Second, is it linearly independent? Like if you have I and J, is one of them a multiple of the other one? Obviously not. One is not the multiple of the other one. What was our check, our official way of checking things? If I want to see if these vectors are independent or not, I make a linear combination of them and try to make 0. That linear combination, I say let's take sum of I, let's say AI, and some B, some J, Bj. How can I make 0 out of this? 0 means 0, 0. Well, this is A times 1 and 0, and this is B times 0, 1. If I want to insist for the total to be 0, 0, how many A's would I need? What would be A? Let's just multiply this out. This A times 1 is A times 0 is just 0. B times 0 is 0, B times 1 is just B. I want to create 0, 0 out of it. Let's just add them up. This is AB. I want AB to be 0, 0. What's my only choice? A has to be 0 and B has to be 0. This tells me the only way to create the origin out of these two vectors is to take none of that and none of this. 0 of this, 0 of that. The fact that we arrived at these two being 0 and no other choice tells me that I and J are independent. If I had some other choices, I knew that was a red flag, that they are dependent. Some of them could be dropped in favor of the other ones among them. Okay, they are independent and they span R2. So that tells us, according to this definition, anything that the property that you can span the whole space, the given space, and they are linearly independent, you call them a basis. So here we express this fact like this: Ij, this set Ij, is a basis for R2. Well, we knew that kind of sense that already, but now we made the definition clear. Well, what is it that is facing us? Well, this was rather simple, trivial situation. What if two vectors that were given were not as easy as just I and J? How can we come across the same kind of a verdict? Or, to make the matter worse, what if we were in R3, R4, and so on? How would we make our decision in any of these cases? Well, in general, figuring out if something is a basis or not is going to be a kind of lengthy process, as you might suspect. It's going to require a full-scale Gaussian elimination work, and well, that is what you need to do. So let's see if we can take some examples and okay, let's start with problem 1. It says I give you a bunch of vectors u1, u2, u3. Question: do the collection of u1, u2, u3 form a basis for R2? Is this a basis? What do you think? Remember, basis requires two requirements. First of all, you should be able to build up your entire space out of them. Like, you should be able to build entire R2 from these three. And the answer to that, so there are two questions. U1, U2, U3. Question 2. What is question 2? Very good. Are they linearly independent? One of these questions is easy to answer. They are dependent because 3. Yeah, we said last week, last class, that if you have more vectors than the components, then they are automatically dependent. We didn't show the proof, but I asked you guys to read it. It's very straightforward. If you got 3 vectors in R2, there isn't room for them to become independent definitely one of them is going to be a linear combination of the other ones, or perhaps two of them are copies of the third. So are they linearly independent? And the answer here is no, because in 3 vectors in R2 are always dependent. You don't need to check. In general, n vectors in Rk are linearly dependent if what? What should be the connection between the number of vectors and number of components? If you got more vectors than you got components to allocate, you know, it's like you got 3 rooms and renting it to 5 people. They have to share somehow. So there isn't that enough space for them to be independent. This is the general principle that we have. So we already know the answer is negative, and so we already can say, do they form a basis for R2? And the answer is no, because they have extra fat in them. Okay, basis has to be trimmed down, just the minimal that you need, no more. We could go and investigate that question. The answer is most likely, looking at them, is the answer is positive, but why spend more time on it? We already gave the answer to the question. That's 1. Any question on that one? 2. V1 So at this stage, let's just do problem by intuition and inspection, and later on we'll have enough cases where we have to actually labor on these things to answer. I'm given 2 vectors, and the question is that would they form a basis for R3? So the question is V1, V2, is it a basis of R3? What do you think? If I'm given 2 vectors, if I take a linear combination of these 2, can I reach every point in this room? If I have, so here is a 3-dimensional setup, and say you have 2 vectors in it. Can you reach every destination in R3 by just making a combination of this red and the green one? What do you think? Well, yeah, the set of linear combination of these 2 is going to be this plane that contains those 2 vectors. I drew them so that it kind of suggested that, say, we are on the XY plane. If you got 2 vectors, at most you can cover something that is 2-dimensional. There isn't anything to help you to get out and cover the section of space that is high up here. This is not covered. So what we say right now is that the answer is no, and this time the failure is happening on the following issue. Can we build the entire R3 from this? No, because V1, V2 do not span R3. Okay, so again we are just saying by inspection for now, but so those of you who have the book, what would be the answer to question 3? You have W1, W2, W3. I write just some of these numbers. Here we are given 3 vectors in R4. What is your guess now? Would that constitute a basis? So this is argument based on dimensionality. I understand we didn't go through it sufficiently enough, but if you have too few vectors, if you have fewer than this, is not a basis because it doesn't cover the whole space. If you got more than this, it's not a basis because somebody is extra, you can trim that person. Okay? So if the number of vectors you got, like here you've got 3 vectors, but it is a 4-dimensional space. This is not enough to cover the whole space. And what if I had 5 vectors? If I have 5 vectors, there are too many of them. At least one of them is redundant, perhaps more. So the issue that is tough to answer is, what if I had 4 in a 4-dimensional space? Or what if I had 3 in a 3-dimensional space? So this is argument about the basis by just simple counting. You understand that? It's very easy to do and there isn't any work to be done. But as you might suspect, we have some tough lessons to cover. So say problem, say 8. I am given vector v1 is 2, 2, v2, there is a typo here, but that's not important, minus 3, minus 3. Question is v1, v2 a basis, let me not call it B, a basis for R2? What would you think in this case? No, because? Excellent. So in this case, we see right away. They say that is 2, 2. This is minus 3, minus 3. They are not linearly independent. So everything else out of the window. This is not linearly dependent. Very easy to see. For example, V2 is minus 3/2 of V1.
Is that not linearly dependent?
They are linearly dependent. They are linearly dependent, or they are not independent. Well, let's make it explicit. V2 is just a copy of V1. It's just stretched the other way, but just a copy of V1. So in any case, one of these guys is redundant. As soon as that happens, it's not a basis. You don't need to go cover the other issue. We don't need to go work on the issue of span. And this thing is not going to span the space anyway, but we don't even need to answer that. So how about let's back up to something that's going to take us a little bit longer. U1 is equal to 1, 2. U2 is equal to 2, 1. Is this a basis for R2? What does the picture tell you? Here's 1, 2. 2, 1. Do they look like linearly dependent on each other? No. These two, one is not a multiple of the other one. They are linearly independent. Does it look like you can build up the whole space with them? If you have any point, any vector here, you want to know how many of this, how many of that it takes to build this. Here is something from basic geometry. Make a parallelogram. Take that vector, resolve it along these two. see how much bigger this one is compared to U1. Say it's 1.5 U1. That's how many U1 you need. Check these things, how many bigger than U2 that is. Say that is twice U2. So that tells you 1.5 U1 plus 2 U2 is going to build that vector that you want. So this is answering the problem by just visual inspection. That is good for small spaces, something that you can draw. Essentially just good for R2. But we want to build the techniques that's going to be available to us in R3 or higher dimensions or situations where visual inspection is not easy. So how do we do that? So here is a kind of official approach. Do they span R2? Okay, visually you said yes, but do you want to know what if I couldn't see? What if it was a high dimension? What if these two vectors kind of close to each other? What do I do in that case? I say consider an arbitrary element. Okay, like this vector that we picked here, consider you just pull this guy out of the hat. Okay, so its elements are not specified to be anything special. Let's call it x1, x2. Consider an arbitrary vector x1, x2. Or let me call it some other lettering so that the approach that you take when you are comparing with the yeah, that's good enough, I guess. The book is also calling it x1, x2. Consider an arbitrary vector x1, x2. Is it a linear combination of U1, U2? Two things to answer. Is it linear combination? Yes or no? That's step one. The problem might be a little bit tough to say. What if it is? Tell me explicitly what linear combination of U1 and U2. So it might be asked, what linear combination? If yes, give explicit combination. What does that mean? Let me start a new page. So we're running out of space here. So let's remember, U1 was 1, 2, U2 was and we have some vector x1, x2. I want to write this that is, this vector is given to me. I'm asking how many of these things should I pick. So say out of vector U1, tell me how many of that I need. Tell me how many of this one I need. So given x1, x2, find c1, c2 if they exist. Okay, so let me remind you again, what's the deal here? Some vector is given, some arbitrary vector is given. The question you are facing, can this thing be built out of a linear combination of these two? The idea is that, for example, you're taking V1 and stretch it by some factor like C1, V1. Taking V2 and stretch it until you come here, that is C2, V2. Such that, excuse me, your U1 and U2, let's see, U1, U2. Such that when you add these two, you get your original vector here, V. Can this be done? And if so, explicitly tell me what is C1 and C2. So we go back and say, okay, you want to create this out of linear combination of those two. So let's go ahead and write a linear equation. How does that go? C1 times 1 C2 times this is 2C2 and C2. I want to create x1 and x2. What does that mean? This is C1 plus 2C2 has to be x1. And 2C1 plus C2 has to be x2. Well, that is a linear system. We go ahead and solve, just that you shouldn't get confused. Find, who are we finding? Find C1 and C2. In terms of what? In terms of x1 and x2. So the only way this is different from the equation that you have seen is that right hand side is the address of that arbitrary vector. Instead of choosing a specific, you're just letting it to be free, just some x1 and x2. You have to go ahead and find the coefficients C1 and C2 in terms of x1 and x2, meaning in your answers there's going to be a mix of these things. Well, how do we do that? This is a 2 by 2 system. You can do Gaussian elimination. You can do, let's see. What is the coefficient? Here's 1, 2. Right hand side is x1. This is 2, 1. Right hand side is x2. What kind of step do we take first? Try to get rid of that entry. Is that right? How do you get rid of that entry? Subtract twice row 1 from row 2. Is that right? So what does that give you? So 1, 2, x1. When I add minus twice the first row to the second row, this entry becomes what? 0. This entry becomes negative 3. This entry becomes x2 minus 2x1. Is that right? Or just carry out the equation as them c1 plus 2c2 is equal to x1. Add minus twice equation 1 to equation 2, which gives you minus 3c2 is equal to x2 minus 2x1. Okay, what does that tell me about, so either that style or this style. What does that tell me about C2? It's going to be right hand side x2 minus 2x1 over minus 3. Is that right? Let's write it a little bit nicer perhaps. C2 multiplied by minuses 2x1. Excuse me. Is that right? How do I get C1? Well, that's going to be x1 minus 2c2. So that's going to be x1 minus C2 is this. Now help me simplify this. I take a common denominator. This is 3x1 minus 4x1 plus 2x2. So that simplifies to 2x2 minus x1 over 3. So here let's paraphrase. C1 turned out to be 2x2 minus x1 over 3. And C2 turned out to be, here C2, 2x1 minus x2 over 3. What does that mean? First of all, we proved that whatever vector you take on the right hand side, there is a combination of the, okay, let's go all the way back here. This was some arbitrary vector that was given to me. I managed to find C1 and C2. that tells me whatever vector you give me, I can cook up a combination of these two to create that one for me. That tells me I can span that space. I can span that space. Let's write it out explicitly. What we found out that x1, x2 is equal to, what was this here? C1 times 1, 2. C1 was 1, 2. And here's the C1, 2x2 minus x1 over 3. Plus C2, which is 2x1 minus x2 over 3. So you tell me I want that. Tell me how to cook that up. Here I tell you, here's your vector u1, here's your vector u2. Take these many of u1 and these many of u2, and you are done. So what that tells me is that u1, u2 spans R2. Item number 2, we have to check, are u1, u2 linearly independent? How do you check that? The way you check it, you say, what combination of u1 and u2 is going to give you 0? Well, what is 0? 0 means 0, 0. So, you are asking this specific question. Construct the origin for me. Construct the 0 vector. Well, 0 vector means x1 is what? 0. x2 has to be 0. So it tells you the only way to make 0, 0, the only way to make 0, 0 is what? Take 0 of the first vector and 0 of the second vector. So in one stone you're killing two birds. That is, the only way to create 0, 0 is to pick none of this and none of that. That tells you x1 and x2, both of them, that these coefficients, actually c1 and c2, both of them have to be 0. That tells you, yes, they are linearly independent. So we did two things. It spans R2 and they are linearly independent. If it has both of these two properties, therefore we can call it a basis. Now again, you are going to say, well, I could see that in the picture. The issue is that if it was three-dimensional or more, you couldn't see. And also you want to have mechanism that, say, a computer can duplicate as well and come up with the same answer instead of just relying on your visual impression. So from this section, you want to do a few exercises, and let me ask you to concentrate on problems from 1 through 16, from 197. We have a lot more to say here. It's going to take a while to finish this section. So I'll see you, I guess, on Monday.
Just move it up a little bit.